Okay, so we're going to use the definition of electric current. Electric current is the rate of flow of charge past a given point. So that means that the current, I is the symbol for current, is equal to the charge Q, which will be in coulombs, divided by the time T, which should be in seconds. If it is coulombs per second, that'll give us the current in amperes. Alright, so we've done the part above here. Current is said to exist whenever, again, it's the electric charge has to move, has to flow, and since it has to come back to the battery, it's going to have to flow in a loop. That's why we call it a circuit. The word circuit really just means to go around. So we're going around one time. As a quantity, electric current is defined as, again, it's divided by the time, so that means rate, and it's the rate of which charge flows past a given point. Charge is symbolized by Q. So that's going to be letter C there, the rate at which charge moves through a cross-sectional area of a wire. Okay, we're going to apply that to some basic electric circuit. And again, we're going to use I equals Q over T. Now, if you don't like to run the math on that every time, you can set yourself up a little triangle. People who study electricity often set themselves a series of different triangles. I is equal to Q over T. Alright, so a current, 4A, a current of 1 ampere is a flow of charge at a rate of how many coulombs per second? Well, 1 ampere here would be a flow of 1 coulomb per 1 second. So in that case, everything's just 1. That's the definition of an ampere. B, when a charge of 8 coulombs flows past any point along a circuit in 2 seconds, the current is. So current is I. I is going to be the charge in coulombs divided by the time in seconds. So that's going to be 8 coulombs divided by 2 seconds. That's 4 amperes. If a charge of 5 coulombs flows past point A in our diagram in 10 seconds, then that makes the current. So the current I is equal to the charge 5 divided by the time 10. So 5 coulombs in 10 seconds equals 1/2 of an ampere, or 0.5. D, if the current at point D is 2.0 amperes, then how many coulombs of charge flow past point D in 10 seconds? This time we're actually trying to figure out what the Q here is. So if I want to know Q, I'm going to take the charge, the current I, and multiply it by the time T. So I got the current 2, and the time is 10. So Q is going to be equal to 2 times 10, which is 20 coulombs of charge going past that area. If 12 coulombs of charge flow past in 3 seconds, so that's going to be 12 divided by 3 equals 4 amperes. Point A in 3 seconds, then 8 coulombs of charge will flow past point E in. Now if you look at our circuit, charge flows out of the negative terminal and comes back to the positive terminal. In a single loop like this, the charge must be conserved. So however many amperes go across point E must also be the same as go across point A. Well, in the first part, we figured out that the charge across point A is 4 amperes. So that means 4 amperes of current have to be equal to 8 coulombs of charge, and then we have to find out the time it will take. So in this case, the time would be 8 coulombs over 4 amperes, which is going to be 2 seconds. Now, if we ask any point along that particular circuit, the current has to be the same everywhere because it's only one loop. So the ratio of charge to time has to stay 4. So at any point, those two have to be the same. Okay, and finally, the current at point E is considerably less than the current at point A since charge is being used up in the light bulb. Again, this goes back to our initial discussion of defining current. No, current is never used up. Current is based on charge. Charge is conserved. So the charge can't get used up. It's the energy that actually changes, not the charge. So it's not the current that we're changing, it's the potential that the current has to do work. It's the energy that we're changing. So if you go back to the circuit and try to tie in our ideas of potential difference and potential with current flow, we have the highest potential here, the lowest potential here. As we go through the light bulbs, then we're going to drop, we're going to lose potential. So there'll be a potential difference across each light bulb. And the amount of potential difference will depend on how much resistance the light bulbs have, etc. But the total current that flows through that wire has to be the same. There's no place for it to branch off or change. And charge is conserved, and therefore current, in this case, is definitely conserved. It's the same everywhere in that simple circuit. Okay, so that's how we calculate current. The last thing, we'll look at how fast current moves and why we can turn lights on in an instant.